Hey Mom, today we're starting our math courses. Um, I'd like to introduce you to logical foundations. I figured it'd be best if we started with statements and how to use logical operators such as and, or, and not, as well as truth tables. That's where I started off whenever I did Intro to Advanced Mathematics, and so I thought that would be best for you to start off as well. So let's get right into it. Statements are anything that can be true or false. For us humans, we tend to phrase them as sentences. Computers might phrase them as zeros and ones, and we'll see later that mathematicians usually phrase them as like equations and stuff. But mathematicians use sentences too. Some good examples are Mr. Hockaday is taller than his mom, which is true. All dogs have brown fur, which is false. Clifford is a big red dog, so that's not true. And bananas taste good, which is subjective. It is a statement, but depending on who says it, it can be true or false. But it can be both true or false. Um, if I say bananas are good, I think bananas taste good. But if I've eaten 10 bananas, I probably don't think bananas are good anymore. Ideally, mathematicians like to avoid statements that are subjective. We want statements that are either true or false and do not depend on the person who says it, or when they say it, or where they say it. So let's come up with some good banana alternatives. Oh right, I forgot. I colored these. This one's orange because it's so subjective. Let's come up with some objective banana statements, um, such as everyone anywhere is always in the mood for a banana. This is a subjective statement. This is objective statement. This is an objective statement because uh, it doesn't matter who says it. We're talking about everyone, right? So if you don't like bananas, then already it's false. But if you do like bananas, well, you know someone who doesn't like bananas, so it's false. It doesn't matter who you are, as long as everyone is always in the mood for a banana, or someone isn't in the mood for a banana. That's what determines whether it's true or false. Mr. Hockaday ate a banana on New Year's Eve is also false. Um, it's also objective as well, because it's about one specific person, me. Um, that's why Mr. Hockaday is taller than his mom uh, is an objective statement. Um, but if I said I am taller than my mom, it would be a subjective statement because depending on who said that, it would change the definition of who is I and who is my mom, and it would make the statement mean something different. So it would be true or false depending on that context. Um, some people want a banana for Christmas. If you find one person who wants a banana for Christmas, this becomes true. It does not matter who says it. It does not matter who is who. It does not matter who says it because we're talking about the general pool of all human beings, and we're saying, does one of them want a banana for Christmas? At least one, maybe more. If that is the case, then this is true. If no one wants a banana for Christmas, then this is false. Mathematicians like to work with objective statements, like 2 plus 5 equals 25. Statements don't have to be true, though. This is false. No matter what language you say it in, no matter who says it, this is objectively false. As long as we agree on the definition of addition and equality, this is false. Luckily, in mathematics, we tend to just wind up dealing with objective statements. But sometimes it is a thing you have to look out for. So let's go on to logical operators. And, not, and or. We'll be using two statements, one that is false and one that is true, obviously. All pigs can fly is a false statement because there are some pigs who can't fly. My mom is awesome is obviously a true statement because have you met her? She's amazing. Although I suppose it is subjective as well, but I think all moms are awesome in their own ways, unless they're not. Anyway, let's ignore that for now. Uh, and or are binary operators, which means they take two statements and combine them in some way. Not is not a binary operator. Not applies to one statement at a time. So if I say not all pigs can fly, that would be true because all pigs can fly is false. Not essentially reverses the true or false value. So if a statement is true, then the negated version of that statement will be false. If a statement is false, the negated version is true. If I say all pigs can fly and my mom is awesome, well, that statement can only be true if both of those are true. We already know that all pigs can fly is false, so unfortunately, this statement is false. However, all pigs can fly or my mom is awesome, that's true as long as one or both of those statements is true. My mom is awesome, after all, so this statement ends up being true. These can get a little muddy, so we're going to start using symbology. I like to use letters like P, Q, and R to represent logical statements. It helps you generalize them so that you can instead focus on their interactions. Such as, what happens when we do P and Q? When is that true and when is that false? In our next slide, we'll talk about truth tables, where we go through all the different permutations of P and Q. Some examples of using symbols would be to say not P. Essentially, that would be true whenever P was false. P and Q would be true whenever P was true and Q is true, etc. Truth tables. Awesome. This leftmost column here are all the possible values of P and Q. Right. So you'll see that there's 2 T's and 2 F's in each column. The first row is when P is true and Q is true. The second row is when P is true and Q is false. The third row is when P is false and Q is true. And the fourth row is when both of them are false. Using these truth tables, we can assess the validity of these 3 columns, 3 through 5, for each row. How true is that statement based on the values of P and Q given in that row? For example, if I'm looking at P or Q, so that's the 4th column, and I want to know what happens when P is true and Q is false, well, I go to the 4th column, and I go to the 3rd row, and I see, okay, when P is true and Q is false, then P or Q must be true. Truth tables are really useful for organizing this kind of information and helping you sort out what's going to be true and what's going to be false given a certain statement with these logical operators, right? And they get complicated pretty quickly. Like, look at this last one. Not P or Q. I wrote that it's true, false, true, true, but we need to verify that. So let's go to the next slide and double check that I'm doing the right math. Here, I've added a column, the 3rd column, that says not P. Not P is essentially the opposite of P. So whenever P is true, not P is false. And whenever P is false, not P is true. So what we're going to do is we're going to go through row by row through Q and not P. And we're going to test the validity of this last column, not P or Q. So for the first row, Q is true and not P is false. So not P or Q can be true because one of those is true. Let's skip the second row for now. The 3rd row, Q and not P are both true, which means that not P or Q, must be true, because one or both of them ended up being true. The same thing is true for the fourth row, because not P is true. So Q is false and not P is true. That means that not P or Q is going to be true, because not P ended up being true. And then for that second row that we skipped, both of them are false, which means that this statement is false no matter what. Notice that we didn't even have to think about P. We just focused on not P, because that was our first half of that little equation. Not P or Q. It's not an equation, it's a statement. Whatever. Okay, so to recap, today we learned how to write statements, how to use and, or, and not operators, how to use a truth table. Dang it, I keep doing that. When I practice this, I keep acting like, oh, and there's a fourth point. There's not. Our homework, your homework, for the next time, next video, I want you to write a truth table for the following statements. These of them. I'm not going to read them. You can read them. Notice the parentheses. These parentheses are important. Whenever you see something like not, parentheses, Q and P, that means solve Q and P and then do the negation of that. So not Q and P is essentially the opposite of Q and P. So just a little hint for when you're solving these on your own. All right. See you next time. Bye.